Good morning all. પ્રીવિયસ લેક્ચરમાં આપણે સ્પેસ અને સ્પીડ વિશે થોડી વાત કરી હતી, બરાબર છે. અને એની આગળ આપણે ડેન્સિટી એન્ડ ઓક્યુપન્સી થોડું ડિસ્કશન કર્યું હતું કે વોટ ઇઝ ડેન્સિટી એન્ડ વોટ ઇઝ occupancy. So the density is the third primary measure of the traffic stream. Characteristic is defined as a number of vehicle occupying a given length of a highway or a lane, generally expressed as a vehicle per mile or the vehicle per mile per lane. And the occupancy is, while density is difficult to measure directly, modern detectors can measure occupancy. બરાબર. તો occupancy કેવી રીતે થાય કે ભાઈ જસ્ટ આ જેમ કે ફિગર તમે ધ્યાનમાં જુઓ છો, બરાબર, તો આ આપણું ડિટેક્ટર છે, બરાબર, એની કંઈક લેન્થ છે LD, બરાબર. વ્હીકલ જે છે, બરાબર, આ ડિટેક્ટર આપણું કેટલા ટાઈમ માટે ઓક્યુપાઈડ રહે છે, બરાબર, તો એના ઉપરથી આપણને ટોટલ ઓક્યુપન્સી મળે, બરાબર. લાઈક આપણે અહીંયા ટ્રાફિક સિગ્નલ છે અને અહીંયા આખું ડિટેક્ટર્સ થી આપણે ફીલ કરી દીધું છે કે ત્યાં મૂકેલા છે આખા ડિટેક્ટર્સ, બરાબર છે. સો ડિટેક્ટર્સ મૂકેલા છે તો એના લીધે તમારા જે વ્હીકલ સ્ટોપ થાય છે, તો જે ડિટેક્ટર જેટલા બી ઓક્યુપાઈ થાય છે, બરાબર, ફોર ધ પર્ટિક્યુલર ગિવન ટાઈમ, સો દેટ ઇઝ કોલ્ડ ધ ઓક્યુપન્સી, બરાબર છે. So next our topic is spacing and headway. So while flow, speed and density represent a macroscopic descriptors for the entire traffic stream, they can be related to microscopic parameters that describe individual vehicles within the traffic stream or specific pairs of vehicle within the traffic stream. Next is spacing. Spacing is defined as the distance between the successive vehicle in traffic lane measured from some common reference point on the vehicles, such as the front bumper or front wheels. The average spacing in a traffic lane can be directly related to the density of lane. D is equal to 5280 divided by dA, where D is a density and DD is the average spacing between the vehicles in the lane. Headway is defined as a time interval between the successive vehicle as they pass a point along the lane, also measured between the common reference point on the vehicles. The average headway in a lane is directly related to the rate of flow. V is equal to 3600 divided by HD. So V is a rate of flow and HA means average headway in the lane. Use of the microscopic measure. Microscopic measure are useful for many traffic analysis purposes because a spacing and or a highway may be obtained for every pair of vehicles. The amount of data that can be collected in a short period of time is relatively large. A traffic stream with a volume of 1000 vehicles over 15-minute time period result in a single value of a rate of flow. Space means speed and density when observed. There would be, however, 1000 headway and spacing measurement assuming that all the vehicle pairs were observed. Use of the microscopic measure also allow various vehicles types to be isolated in the traffic stream. Passenger car flow and densities, for example, could be derived from isolating spacing and headway for the pairs of passenger cars following each other. Heavy vehicles could be similarly isolated and studied for their specific characteristic. The successive chapter illustrates such a process for calibrating basic capacity analysis variable. Average speed can also be computed from the headway, and the spacing measurement are as S is equal to dA upon HA upon 1.10. Okay. So a sample portion, a traffic in a congested multi-lane highway lane is observed to have an average spacing of 200 feet and an average headway of 3.8 seconds. Estimate the rate of flow. So rate of flow after find करवो है तो 0. S is equal to 0.68 200 divided by 3.8 35.8 minute per mile per hour. Next is relationship among flow rate, speed, and the density. The three microscopic measures for the state of a given traffic stream, flow, speed, and density are related as V is equal to S into D, where V is a rate of flow, S space means speed, and D is a density, vehicle per mile or vehicle per mile per lane. Space means speed and density are measured that refer to a specific section of a lane or highway, while flow rate is a point measure. Figure illustrate that the relationship. The space means speed and density measured must apply to the same defined section of a roadway. Under stable flow condition, the rate of flow computed by equation applies to any points within the section where unstable operation exists. The computed flow rate represent an average for all points within the section. If a freeway lane were observed to have a space mean speed of 55 mile per hour and density of 25 vehicle per mile per lane, the flow rate in the lane could be estimated v is equal to 55 into 25, 1375 vehicle per hour in a lane. As noted previously, this relationship is most often used to estimate density, which is difficult to measure directly from the measured values of a flow rate and the space mean speed. Consider a freeway lane with a measured speed means space mean speed of 60 mile per hour, or the and a flow rate of 1000 vehicle per hour in lane. So the equation goes to D is equal to 16.7 vehicle per mile per lane. Equation suggests that a given rate of flow could be achieved by infinite number of speed and density pairs having the same product. Thankfully, this is not what happens, as it would make the mathematical interpretation of traffic flow unintelligible. There are additional relationship between pairs of these variables that restrict the number of combinations that can and do occur in the field. The exact shape and calibration of this relationship depends on the prevailing condition, which vary from location to location and even over time at the same location. Note that a flow rate of 0 vehicle per hour occurs under two very different conditions, where there are no vehicles on the highway, density is 0 vehicle per mile, and no vehicles can be observed passing a point. Under these conditions, speed is unmeasurable and is referred to as a free flow speed, a theoretical value that exists, a mathematical extension of the relationship between speed and the flow. In practical terms, free flow speed can be thought of as the speed a single vehicle could achieve when there are no other very vehicles on the road and the motorist is driving as fast as practicable given the geometry of the highway and its environmental surrounding. A flow of 0 vehicle per hour also occurs when there are so many vehicles on the road that all motion stop. This occurs at a very high density called the jam density, and no flow is observed as no vehicle can pass a point to be counted when all vehicles are stopped. Between between these between these two extreme points on the relationship, there is a peaking characteristic. The peak of the flow speed and the flow density curve is the peak of the flow speed and the flow density curve is the maximum rate of flow or the capacity of a roadway. Its value, like everything else about this relationship, depends upon the specific prevailing conditions at the time and the location of the calibration measurement. Operation at capacity, however, is very unstable. At a capacity with no usable gap in the traffic stream, the slightest perturbation caused by an entering or a lane changing vehicle or simply a driver hitting the brakes cause a chain reaction that cannot be damped. The perturbation propagates upstream and continues until sufficient gap in the traffic stream allow the event to be effectively dissipated. The dash portion of the curve represent unstable or forced flow. This effectively represent flow within a queue that has formed behind a breakdown location. A breakdown will occur at any point where the arriving flow rate exceeds the downstream capacity of the facility. Common points for such breakdowns include on ramps or on freeways, but accidents and incidents are also common. Less predictable causes for the formation of queues. The solid line portion of the curve represents a stable flow. Except for capacity flow, any flow rate may exist under two conditions: a condition of relatively high speed and the low density, a condition of relatively low speed and the high density. Obviously, traffic engineer would prefer to keep all the facilities operating on the stable side of the curve, because a given volume or flow rate may occur under two very different sets of operating conditions. These variables cannot completely describe flow conditions, nor can they be used as measure of the quality of traffic flow. Values of speed or density, however, would define unique points on any of the relationship of the figure, and both describe aspect of quality that can be perceived by drivers and the passengers. Over the years, various researchers have studied the speed flow density relationship and have attempted to develop many mathematical description for this curve. In the 1930s, Bruce Greenshield conducted the first formal studies of the traffic flow. Sorry. he hypothesized that the speed density relationship was linear. Later, Ellis suggested a piecewise linear relationship using 2 or 3 linear relationship for the various portion of the speed density curve. This approach created discontinuation curves within the critical discontinuity in the vicinity of the capacity. Greenberg hypothesized a logarithmic curve for speed density, while Underwood used an exponential model for this relationship. Eddy suggested discontinuous relationship for speed density using both exponential and logarithmic relationship, and may suggest a bell-shaped curve. Reference 6 reports on a classic study in which all these mathematical description were compared using a single set of data from the metric parkway in the Connecticut, Carica. All these historic studies focus on the calibration of the speed density relationship. This is considered to be the basic behavioral relationship, drivers selecting speed based on their proximity to the other vehicles. ઓકે સો આખી બધી જે થિયરીઝ હતી એ બધી ડિફાઇન કરી એ લોકોએ અને એના પરથી કેલિબ્રેશનનું એક આપણને ટૂલ મળ્યું. ઓકે સો અહીંયા આપણું આ ચેપ્ટર કમ્પ્લીટ થાય છે ટ્રાફિક સ્ટ્રીમ કેરેક્ટરિસ્ટિક. ઓકે સો નેક્સ્ટ આપણું જે ચેપ્ટર છે એ આપણે નેક્સ્ટ લેક્ચરમાં સ્ટાર્ટ કરીશું. ઓકે સો સી યુ ઇન ધ નેક્સ્ટ લેક્ચર. થેન્ક યુ.